Lesson 12.3 Single Slit Diffraction. People discovered that when a wave goes through an opening, it bends a little bit. And the amount of bending is related to the ratio of the wavelength to the width of the slit. A large opening, compared to the wavelength, makes a small bend. A small opening, compared to the wavelength, makes a large bend. This bending is called diffraction. Single slit will produce a diffraction pattern with light. The Huygens wavelets interfere with each other. But what happens with single slit diffraction compared to double slit or multiple slit diffraction is that the center bright band is twice the width of the other bands. So now instead of measuring where the bright spots are, we're going to measure where the dark spots are. The first order dark band is going to occur when the left edge and right edge of the paths differ by 1 wavelength. That way, this beam from the left and the right, they differ by 1 wavelength, which is, you'd think, constructive interference. So think about just right before they differ by 1 full wavelength, because halfway in between, they differ by half a wavelength. So the center wave differs by half a wavelength, which has the destructive interference. So those two paths have the destructive interference. And then so the path from point 2 and point 4 are going to differ by half a wavelength. And they're going to have destructive interference, and so on. So at that angle, all you get is destructive interference. So it turns out that sine of the angle equals the wavelength over the width of the slit. For multiple dark fringes, we will then multiply it by the m, which is the order of the dark fringe, first, second, or third one. Why is it sine of the angle? If we look at this triangle right here, it's a right angle. That's theta. So sine is opposite over hypotenuse. Opposite being a wavelength, the hypotenuse being the width of the slit. So theta is the angle between the wave and the normal to the slit. The m is the dark band order, lambda is the wavelength, and w is the width of the slit. So let's say a laser shines through a single slit width of 3.25 times 10 to the negative 6 meters. The first order dark fringe is 10.2 centimeters from the center, and the slit is 50 centimeters from the screen. So we could draw a nice little right triangle. And it says the first order dark fringe is 10.2. So here's m equals 1. Here's the center, m equals 0. And we're 50 centimeters from the screen. So this is the screen over here. This is our slit and our laser shining through our slit. So from there, since it's a right triangle, we can say tangent of our angle is the opposite over the adjacent. Use inverse tangent. And you should get about 11.53 degrees. So now we know our angle. So now we can use the sine of our angle equals m lambda over w. So sine of 11.53 equals 1 times, we're looking for the wavelength, And it says our width is 3.25 times 10 to the negative 6 meters. All right, multiply. And you end up with 6.50 times 10 to the negative 7 meters for lambda, which would be the same thing as 650 nanometers. An application of this is microchip production. So when you're talking about very small electrical components and very small circuits. So how they make these microchips is they make masks similar to photographic slides, so the light will shine through it. So a light shines through the mask onto a silicon wafer coated with photosensitive material. The exposed portions of the light are chemically removed. But if too much diffraction happens, then the lines overlap and your circuit doesn't work. Currently, they use UV rays, which have a smaller wavelength than visible light, to minimize this ratio. To improve it, they could use X-rays or gamma rays or even smaller wavelengths, but of course, those are more dangerous. Turns out that if light goes through a circular aperture, a circular opening, it also has diffraction. So this is true from light coming from lenses and mirrors. For circles openings, the first minimum will occur at 1.22 wavelength over the d, which is the diameter. Now notice though, the angle is in radians because we're using a small angle approximation. The diffraction limits the amount of detail or resolution. So these pictures of these lights are taken, they're both two circular lights, like two flashlight beams or two car headlights. And so the one on the far left, they're a long distance away. They look like there's just a single light. And then the one on the right's a little bit closer than the one in the middle is the closest. So we say the two images are just resolvable when the center of one diffraction pattern is over the first minimum of the other. So the one on the right is the one that is just resolvable. We can just start to see that there are two circles there. So what is the minimum angular spread of a 633 nanometer wavelength helium neon laser beam that is originally 1 millimeter in diameter? Okay. Well, since it's circular, we're going to use this one. The wavelength is 633. It's nano, so times 10 to the negative 9 meters. And the diameter is 1 millimeter, so that's 1 times 10 to the negative 3 meters. And that comes out to be 7.72 times 10 to the negative 4. And that was in radians for the angle. Part B. If this laser is aimed at a mountain cliff 15 kilometers away, how big will the illuminated spot be? Well, we know our angle, so let's just take one of these here and let's make it a right triangle. We know this is 15 kilometers, so 15,000 meters. We're looking for the little y, and we know our angle. So we could use tangent. So we could say tangent of the angle is the opposite over the adjacent. So tangent is 7.72 times 10 to the negative 4 radians. Make sure you're in radians. Py over 15,000 kilometers. Multiply by the 15,000, and you should end up with 11.58 meters for y. So this is 11.58 meters. We can use symmetry and say this is also 11.58 meters. And in the middle was the original diameter, which was 1 millimeter, or 0.001 meters. That's so small compared to the rest, we're going to ignore it. So then our full width is going to just be 2 times 11.58 meters, or 23.2 meters. So that's a fairly large spot starting from 1 millimeter. So you need to be careful for applications like in the military where you use laser-guided bombs or something. What happens is you shine a laser at a cliff or a target that's a long distance away, and the bomb zeroes in on that laser spot. But if that spot can be huge, so you might not hit exactly where you want to hit, which could be dangerous.